So we can put some structure in the search space. It's like a tree. And the idea of the branching algorithm is to explore the tree. Of course, there is a very big tree. If you don't have a way to cut some parts, the algorithm will be very, it will not be easy. So we can fix the first 3 atoms of a protein because we know all of the distance related to the protein. So we are of course we are considered a solutions modulo rotation and translation. So we fix the first 3 atoms of the protein, and we have 2 possibilities for the 4th atom. Suppose now that we explore the tree from left to right. So fixing the, so we are going on this direction. So fixing this and this, we have 2 possibilities for the 5th atom. Until now, we cannot use another information, for example, provided by the NMR, because we are supposing that for each 4 consecutive atoms, we have a click, we have all of the distance. But now, suppose that we have the distance connected this atom to the first one. Yeah? So we can compare the distance that we calculate using this possible position for the 5th atom with the information that we have experimentally. We compare. If the distances are the same, we can continue the search. But if the distances are different, it means that this position for the 5th atom is unfeasible. So we can prune all of this subtree. Okay? So we are supposed exactly like this. So we prune the subtree, we backtrack and try the other way. So in this case, I'm supposed that this position is equal, unless an epsilon, to the information provided by the NMR, and we can continue the search. We have 2 possibilities for this atom, and I'm supposing again that we have a distance from this to other atom. So here we found a solution. So a solution is associated to this path. We can continue our search, and we are supposing that here this position is not feasible with the information that we have. So here we have a solution. Okay? This means that we found the global minimizer. Yeah? 1. But we can continue the search in order to find other solutions, so other global minimizers. So and this is one of the advantages to our discrete approach, because we can find not just one solution, but potentially all the solutions. And if you use a continuous method, you know it's very difficult to find just one global minimizer. So we can continue the search in order to try to find other solutions. So here, it's not a coincidence that you have a symmetry related to this solution in blue to this solution that version proves that the peer algorithm found. And in fact, this solution is related to a symmetry defined by the first 3 atoms. In fact, this means that for every solution that we found here in this half symmetry, there is another one symmetric related to the plane defined by the first 3 atoms. So this means that the quantity of solution is even, right? And of course, this means that it's not necessary to explore this part of the tree. So our first computation results, when we apply the clear algorithm protein, we note that not even the number of solutions is even, but it's power of 2. And we thought that this property would be easier to prove, but we were able to prove just last year using group theory. This is a nice example to say to the students because firstly, this could be just a mathematical curiosity, but Antonio Querido notes that we could use this property in order to design a better BP algorithm. And this idea is what? Because there are other symmetric properties related to this subtree. Because this symmetry, and we call the first symmetry, is related to every instance of DMDGP. But for every instance, there are other symmetric properties related to a specific instance. And the general idea is that it's necessary, because of this symmetry, it's necessary just to find one solution. If you find one solution, all of the other solutions, of course in this picture is not easy to see, but if you find just one solution, all the other can be using symmetric properties that we developed before for the question related to the quantity of solution is power of 2. But this is another question. I don't know if Antonio will present, will speak something about this. In the next presentation, Antonio will provide a lot of nice picture related to proteins and more questions related to the orderings. So, we can skip this. So, our question, the title of the presentation is related to the quantity of solution. We know that the quantity of solution is power of 2. But the question is it possible to calculate exactly the quantity of solution when you found just one solution using the algorithm? And the answer is yes. And in fact, it's nice because this result is just a consequence of the results that prove that the quantity of solution is power of 2. But we could realize, just thinking about the dual space. The dual space is when we just think about the distance, because we can formulate the distance geometry problem in the primary space when you think about the Cartesian coordinates of the points, or just in the dual space when you think about distances. And in fact, the first formulation of the distance geometry was done just think about dual space. And we realized that we can calculate exactly the quantity of solution of DMDGP when we were working with the dual space. Then we got this result, and using the group theory necessary to prove that the number of solutions is power of 2, we could also determine the number of solutions. So first we need to define this operator, the partial reflection operator. And this we are illustrating when k is equal to 3. So first we have given a solution. So in black one, we suppose that we have a solution. And first we have to define a reflection of a vertex v. For example, if we fix v, we consider the 3 immediate predecessor, and we have a plane, and we can reflect each point in the solution related to this plane. Okay? So using this reflection, we can define a partial reflection operator like this. So X is a solution of the DMDGP problem, and V is a fixed vertex, and we can define this partial reflection operator. So in fact, we can define a product of partial reflection operator, consider the composition of two functions like this, and using this multiplication, we can put a group structure in this partial reflection operator. We can prove all of the properties of group. In fact, they are also commutative, so it is a Abelian group. And the first result is that we can use this set, the set of all of the partial reflection operator, and we can generate this group, and this group is associated to the solution of the DMDGP problem when we have just the minimum set of edges. And this minimum set of edges is that we have just the distance related to each 4 consecutive vertices. So this is the group D is related to the discretization edge. So this is the minimum quantity of edge that we have to know in order to discretize the third space. Now, what we want to do is to define a group related to the instance of the problem when we have another edge. For example, the edge provided by the enema. So now I have a picture. I'm going to illustrate this. So suppose that we have in the plane, so k is equal to 2. So So it means that we can fix the first two vertices. And this is the full tree. Why? Because I'm supposing that here we have just the minimum set of edges. Okay? So if we don't have additional edges, all of this paths can be solution. But now suppose that we have just one additional edge. So the edge connecting 1 and 4. So with additional edge, we can prune some part of the tree. In this case, I'm supposing that this position is feasible according to the additional edge that we have. But since in this case we will have two spheres in 2D, we have just one point in the intersection. So it means that the other possibility is not possible. So we prune here, and this is not available. Using the first symmetry, it means that we have another two solution, and this can also be cut. So here it means that in these vertices we can use a partial reflecting operator. This means that we can obtain another solution, but here we cannot use it. This can be pruned. And here, if we are here, we can also use another symmetry defined by the first two points, and we obtain another two solutions. So we can prove using group theory that we can define this in a very generic way. So suppose that we have U and W like an additional edge, and based on this pair, we can define the set S like this. These are the vertices that we can avoid this reflection. So in this case, K is equal to 2, and U is 1. So it means that we have to consider just 4. Yes? So using the definition of this set, it means that if we have UW, in this case 1, 4, we have to avoid 4 in order to reflect, in order to obtain another solution. So this is, of course, it is not easy to see. You can prove using group theory, but it means that given if we have one solution, we can come back vertex by vertices and see if there is another solution symmetric to this. So in this case, suppose that we have this solution. So here we don't have a vertex in order to avoid. We can reflect and obtain another solution without calculating, without using the BP. So we are supposed that we have just one solution, and this another one can be obtained just by using symmetric property. So here, since it is in the set S, we avoid the reflecting. We consider another one, so we can consider this. There are two another solution, and so on. So what we have to do in order to define another group, to define precisely the number of solutions, we have to the group will be generated by this set. And again, using group theory, the number of solutions will be 2 to the power of the cardinality of this set. And this is our final result. Of course, there is some AO. AO is 2 to the power of cardinality of this set. If somebody has more detail, we have a paper and we can explore more of this. And that's it.